Hey, what's up? It's your old pal, Mr. Cook. We got through 14 in the last video. We're going to do this one. I think this one's integral test. I'm pretty confident. Then we got a limit comparison. That integral test, those ones usually take some time. So we'll see how far we get after that. Maybe we'll do up to 18. No, well, we already did number 18. So we'll either do up to number 18 or I'll just stop after 16. It kind of depends on how long this one takes. So let's see what we got. So integral test. I already think that I'm going to have to use integration by parts on this, and I might have to use it twice. So let's first see if we need what we need for the integral test. We haven't done integral tests yet, so let's go ahead and take a look on our little sheet over here. So integral test, as long as the function is continuous, positive and decreasing, we can use the integral test. And what we do is basically we turn the sequence into a function and then take the improper integral, and if it converges, then the series converges. If it diverges, then the series diverges. So, that's what we need to work with here with the integral test. So let's go through the checklist, make sure that everything is working out for our function first. Okay, so if we take the function f of n is equal to natural log of n, so it's equal to the sequence, then we need to check a couple things. First off, what happens to this thing? Is it always positive? Is it decreasing? What's going on with everything? Okay, so first check, is it positive for all n? Well, if I plug in any n values, 1 up to infinity, natural log of 1 is 0, so technically it starts at 0. But every other number becomes positive, because if I plug in 2, it's positive over positive. Or actually, wait, 2, natural log of 2, I think, is actually going to be negative, if I remember correctly. Well, you'll have out your calculator. You can check. So let's see here. What statistics? But natural log of 2. Oh, it's a positive number. Okay, so we're good on that one. It's negative if it's lower than 1. That's right. Yeah, it's like 0.5 or something. So natural log of 2 is positive, so that's okay. So yeah, it'll be positive for any x value that's more than 1, so yes, for n that's strictly greater than 1, it'll be okay. 2, we got to make sure this thing is decreasing. There's a couple ways to show it's decreasing. One way is if you have your graphing calculator, you just graph out the function. So let's see what the function looks like. Is it always going down and to the right? So, oops, I have this in the wrong mode. Sorry, sequence mode. So function mode, there we go. And then natural log of n, x over x squared. All right, what happens to the graph? Well, I got to zoom in a little bit to see what's happening, because it needs to be going down and to the right. Yeah, I can't really tell based off the graph. This is still a little bit not convincing. So you know what? Just so I'm not wasting more time, I'm just going to jump right into another way to see if it's decreasing, and that's by taking the derivative. Okay, so decreasing. So if I take the derivative of my function f prime of n, as long as it's negative for all of the n values that I plug in, then it'll be decreasing for all n. That's relevant for this sequence. So if I take the derivative of this thing, it looks like it's going to be the quotient rule. So I do low d high, so low d high times 1 over n minus high d low, so natural log of n. Or wait, is it high d low minus low d high? No, it's low d high minus high d low. Yeah, that's right. Okay. Then times the derivative of the bottom 2n. Low d high minus high d low, yeah. Over the bottom part squared, so that'd be n to the 4th. And then if you simplify it a little bit, cancel out an n from the top and the bottom. And then n times 1 over n is just 1. Well, yeah, so let's see here. I don't think that this is always going to be decreasing, but it'll be decreasing for a lot of the n's, So if I plug in 1, for example, it'll be 1 minus 2 times 0 over 1, which is positive. But, and even 2, I think, natural log of 2 over 2 factorial, so 2 to the 3rd, so 8. Yeah, I think that's still going to be negative, but once it hits 3, it'll start to be negative overall. Yeah, because I think 2 times the natural log of 3 is more than 1. Let's verify that. 2 natural log of 3. Yeah, so 2 times 2 is 4, so that'll start to be negative for sure. Yeah, so we're just gonna have to say that it is decreasing for n values that are more than 2, I guess. I think so. Yes, and this will be for at least n greater than 2, so that'll work out. And then the next one is that it's got to be positive, decreasing, and then also continuous. And then obviously it'll be continuous because the only non discontinuity that you get is if you had division by 0. But if we're just going from 1 to infinity, we're not going to have 0. And then also natural log is 0. You can't do that, or any negative number. But again, we're not going to have to worry about that with the n values that we're going to plug in. So this is going to be yes, and this will be for all n that are more than or equal to 1. Okay. So it looks like all 3 of these things check out. So that means that we can do the integral test. And what the integral test says is that once all those conditions are met, and that means that all you got to do is just take the integral from the bound 1 to infinity of natural log of n over n squared dn. Okay, and what you do is you just got to see if this thing converges. Well, first off, this is an improper integral, so we got to rewrite this using a limit. So limit as, let's say, b goes to infinity of 1 to b of natural log of n over n squared, and then dn. Okay, so now we're going to do our antiderivative, and we're going to do that off to the side. So side work. All right, so let's see if we just get rid of the bounds on that. So don't write the bounds over here. If you write the bounds, then you're gonna have to do a limit. Okay, so do not write the bounds. We're just gonna do side work and see what happens to this antiderivative. So I would have to use, I think since I have that natural log there, I'm gonna have to use integration by parts. Okay, if the natural log was really easy, like if it was 1 over natural log n natural log n or something like that, something we've seen a lot of, we could use a u sub, but a u sub is not going to be helpful in this case. So you have the u and the dv, and if you remember Mr. Rupp's little Lie thing, then the best thing to use for the u is going to be logs and natural logs. So we're going to use the natural log of n for this. That means that the rest of it, 1 over n squared dn, is going to be part of the dv stuff. So du, derivative of natural log of n, is going to be 1 over n dn. And then dv, so if I take the antiderivative of 1 over n to the second power, in other words, n to the negative second, that'll give me, let's see here, so if I add 1, that'd be a negative 1 power. And then if I divide by that, it's just going to be a negative there. Okay, so that means that this thing turns into u times v, so that's going to be natural log of n over n, and then a negative in front, and then minus integral of v du, so these two together. So that's going to be a 1 over n and another 1 over n, and also a negative on it. So it's going to turn that to a plus, and then dn. So this turns into 1 over n squared, which is really the same thing as saying n to the negative second. So this is going to be a lot easier. Now this becomes negative natural log of n over n. And then antiderivative of n to the negative second would be, if I add 1 to the exponent, it would be a minus, and then n to the negative first. Okay, and then plus c. But since we're doing like a definite, well, an improper integral, we have bounds. We can get rid of that plus c right there when we put this in. So now we did our side work, so now let's go over here. So then we've got limit as b goes to infinity of, and then it's going to be, well, now I'm going to use my antiderivative, negative natural log of n over n minus 1 over n, evaluated from 1 to b. Okay, so then now I'll use fundamental theorem of calculus and plug the b value in. So limit as b goes to infinity of, and then it's going to be negative natural log of b over b minus 1 over b minus, and then now I'm going to plug in 1, negative natural log of 1 over 1 minus 1 over 1. So like this stuff's easy, right? Because natural log of 1 is 0, so that's 0, and then minus 1, so that's going to be a negative 1. But let's see what goes on with this stuff. So if I plug in infinity, oh gosh. Well, I know what's going to happen to this thing, right? So like for this part, limit as b goes to infinity of 1 over b, that just, goes to 0. So that's going to be a 0. Let me kind of erase this stuff so it's not so confusing. And then let's see what happens with this stuff here. So let's see here. As b goes to infinity of negative natural log of b over b. All right, let's see. Well, I know that this one, that'll just, as b goes to infinity, limit as b goes to infinity of b also goes to infinity. And then for this little guy here, this top part will become limit as b goes to infinity of negative natural log of b. That also goes to, well, this will go to negative infinity. Since it's infinity over infinity, we'd use L'Hopital's rule. So that means that we get, let's see here. So limit as b goes to infinity, and then the derivative of negative natural log of b would be, derivative of natural log is 1 over something, so negative 1 over b. Then the derivative of b is just 1. So that means that as b, and divided by 1, just, you don't have to do that. This is redundant. But because of the identity rule, so like as b goes to infinity, this thing goes to 0. So that means that we get 0 plus 1. Okay? So that means that, and let me write this out more formally, because if I wrote all this stuff down, I'd miss a lot of points. But this part's okay. This part's okay here. I'm just like showing what's happening with this. And it ends up just becoming like this part here. So then I get, let's see here. So this is going to be equal to 0. So this becomes 0 minus, and then this is also going to be a 0. And then all this stuff just becomes positive 1. So it just goes to 1. So that means that this thing is going to converge. So the series, my gosh. So therefore, the series converges by the integral test. So this one ended up being pretty nasty because of the integration by parts. And then also it ends up turning into a pretty nasty sequence where we have to, evaluate it using L'Hopital's rule. On a test, I'm sure that we would do something much easier, but you really should start practicing problems that are tough to like get yourself, hardened, like ready to embrace any difficult tasks that you might see on the AP test. So this is still a good problem to practice, but maybe not the level of difficulty that we'd have for you guys on a test, let's say. Gosh, that took up a lot of time. So I'm just going to do that one, and then go to the next video and probably do 3 or 4 problems. Okay, thanks for watching. I hope that was helpful. If not, you can find your math teacher. I'm Mr. Cook. I'll always be available as well before school or after school. Come find me. I'm always willing to help. Thank you very much for watching the video. See you in the next one. Bye-bye.